Dear students, let us continue our video lectures on Advanced Digital Signal Processing course. Let me share the screen. In the previous video lectures, we have seen discrete Fourier series definition and some of the properties. While discussing about discrete Fourier series, we have seen that the discrete Fourier series enable us to compute frequency domain representation for periodic signals by projecting the discrete periodic signals on complex exponentials, discrete complex exponentials. This can also be considered as correlation with discrete complex exponential basis functions, right? Of different frequency. And the synthesis equations, that is, we can get back using these frequency coefficients of discrete Fourier series by back projecting this discrete Fourier series coefficients on complex exponentials. The corresponding samples of the signal. Right? And while in discussion, we have seen that this definition of these discrete Fourier series has come from continuous time Fourier series expansion. Okay, or closely related to continuous time Fourier series. We have also said we can relate this to discrete time Fourier transform such that the frequency like coefficients corresponding to the discrete Fourier series at given k or can be related to sampled versions of the discrete time Fourier transform where omega is 2 pi by n into k, right? So in this video lecture, we will discuss more on the relation between discrete Fourier transform, discrete time Fourier transform and discrete Fourier series representations. Okay, we will also see later. This gives a natural connection to the definition of discrete Fourier transform for aperiodic discrete signals. See the fundamental difference if we see between the definitions of discrete time Fourier transform, okay, discrete time Fourier transform and the discrete Fourier transform. Discrete time Fourier transform is defined for x of n being aperiodic, okay, and finite length. So it can be infinite length as well. So it's let it be aperiodic. Okay, so and this is for x of n or x tilde of n being periodic. Okay, and what now we are saying is, can this be considered as DFS, which is defined for periodic sequences? Discrete sequence gives only a set of discrete frequency quotients, whereas this gives continuous spectrum of Fourier transform or the frequency domain representation. Fine. So now the question is, can these discrete coefficients be thought of as samples in the frequency domain of x of e power j omega or discrete time Fourier transform if under any some assumptions or conditions, because you see that this is a periodic signal and this is an aperiodic signal. Okay, so if they can be related, they can be related under some conditions, right? So what are the conditions under which they can be related, and if they can be related, okay, well, how these can be related? Okay, these are the things that we discuss in this video lecture. Okay, so before we move on, since the finding of the discrete time Fourier transform and discrete Fourier series depends upon the basis functions which are of exponential in nature, let us see how the exponential basis functions can be visualized in Z domain, right? So this is real of Z and this is imaginary of Z. If we write the discrete time Fourier transform expression, so how do I write? E power j omega is equal to summation x of n e power minus j omega n, right? And n ranging from minus infinity to infinity. Okay, so we are finding the projection of sample x, signal x of n on sequence x of n on the exponential e power minus j omega n or e power j omega n, right? So where does e power j omega n can be visualized in this, or e power j omega can be visualized in this Z domain. It can be visualized at the unit circle. So let us visualize it here, because the magnitude of e power j omega is 1. So if you consider Cx of, if you okay, so if you write x of e power j omega, right? So the magnitude of x of e power j omega, okay, can be on the z axis here, okay, which is not shown, which pops up from each of the locations, and this is e power j omega region. Okay, whichever I have plotted here is e power j omega for different values of omega, right? Because for this r equal to 1, okay, is equal to 1, and then omega can be 0 here. For this omega is 0, okay, and this probably omega is 45 pi by 4, okay, and similarly for this omega is pi by 2, and so on. Okay, so you can see that the values, if you consider all the values on this unit circle in frequency domain, what you get is x of e power j omega, right? Okay, magnitude of all this are x of e power j omega, and angle is anyway shown. So angle, since it is a complex number, they will have a complex magnitudes at each of the locations that we see here, right? Okay, so now this is the understanding of x of e power j omega. Fine, now let us come to the discussion on x of x tilde of k. What does x tilde of k does? So if we have x tilde of k, right? So let us write now x tilde of k. What does it do? It also takes the projections of the discrete signal over only one period on set of complex exponential basis which, okay, which are distinct for 0 to n minus distinct values of 0 to n minus 1 distinct values of on omega axis, j omega axis, okay, on unit circle otherwise. Okay, so you have here, so if you would like to see, so you have here, let us take another color. Okay, so here it is x of 0. This is x of 0, x tilde of 0. Okay, so if we take n minus 1, depending upon n, so you have here, okay, or x tilde of 1. Okay, so like this, up to which, like if we have the period of the periodic signal, discrete periodic signal capital N, then you will be taking here n minus 1, 0 to n minus 1, that is n distinct locations. You will be sampling this x of e power j omega. So now let us see, is this really sampling? Okay, and this is the visualization wise you are sampling here to get the frequency coefficients. Okay, so now let us see, under some condition, let us define some common conditions within which we can discuss these relationships. So assume that x of n now be aperiodic, okay, with length equal to m, with having length m. Okay, length of sequence, yeah, that is, if you start from 0, there are m0 to m minus 1 are the possible non-zero locations of the signal. Similarly, if you start from somewhere, n0 plus m minus 1, okay, are the number of non-zero samples that the signal can have. Okay, so the length of the sequence, aperiodic sequence, be n. For that, we will be writing x of e power j omega in this case, right? And let us also assume that we will be constructing x tilde of n. Okay, so let us keep these two different for time being. Okay, later let us see, even if they are same, what is the scenario? If they are different, what is the scenario? X tilde of n is periodic with period n. Okay, both are different for time being. Okay, sequence m, and x of e power j omega corresponds to is its discrete time Fourier transform. Okay, so assume that this is the from this aperiodic sequence we have got DTFT, right? And this x of e power j omega, okay, and x tilde a periodic sequence with period n, and x tilde of k is its DFS. X tilde of k is our discrete Fourier series. Okay, quotients. Okay, now the question is, let's relate this and this. Okay, let us see relation between them. Okay, that's the discussion now, right? We have pictorially seen what do we mean by x of e power j omega and what do we mean by x tilde of k, right? So x tilde of k are nothing but if you have n different samples, so then they are sampled on the like e power j omega axis, that is with magnitude of 1, like, and the angle omega ranging from 0 to 2 pi. And if I want to tell what is the fundamental frequency of these samples on e power j omega axis, what do you tell? Between these two, okay, so how much is this if we call as fundamental frequency, for sampling in frequency domain, for getting the DFS samples, discrete Fourier series samples from x of e power j omega, in that case, this is equal to 2 pi by capital N, right? Because there are n samples total, and the area that, like the region perimeter that it encompasses is 2 pi, 0 to 2 pi are the angles. Okay, so we are sampling n samples from 2 pi, like overall 0 to 2 pi region. Okay, so these are obtained, maybe thought of obtained. So can be thought of by obtained by sampling 2 pi, okay, 0 to 2 pi with n at n equidistant points. Okay, yet capital N equidistant points. Okay, sampling 0 to 2 pi on what? Okay, in frequency domain. Okay, sampling points on right obtained by sampling 2 pi on z equal to 1. Okay, circle, because z equal to 1, mod z equal to 1 forms a circle, right, in z axis at n with n samples, equidistant points. Okay, right. Also, this is what, how you can consider also that we obtained x tilde of k. Okay, so but however, the number of samples with which we have got the x of e power j omega may be different, and the x tilde of k, the number of samples that are there in one period of x tilde of k may also be different, right? This capital N is the number of distinct samples in x tilde of k we have in one period. Okay, so now let us see how this can be related. Okay, so and this can be considered as fundamental gap or distance between two samples in frequency domain, that is omega naught equal to 2 pi by capital N. Right. So let us see, to discuss this. Anyway, we need to sample x of e power j omega. Sampling means what? We have seen that sampling means multiplication with the impulse train, right? So let the impulse train be in frequency domain. Okay. So each impulse train, each of the impulse or the unit impulses here, okay, unit sample sequence in frequency domain are separated by how much? 2 pi by n into k distant, right? And how many samples do we take? 0 to n minus 1, correct? So n samples we are taking. This is what if we multiply, we are saying that we will get something. Okay, so here in this case we are getting x tilde of k. Okay, so this is what the relation that we have written here. Now let us see in time domain what does happen if we do this in the frequency domain. Okay, so please note that this can also be written as, okay, delta of omega minus k omega naught. Okay, where, so instead of k, we can write, since we anyway have a variable k here, let us write this as a variable r. Okay, so r, and this also let it be variable r. Okay, and here also it is variable r. Omega minus r times omega naught. Okay, so right, and this omega naught is equal to 2 pi by n. Okay, because x of n period of x tilde of k is capital N. Okay, based on this, we have got this. These many samples we are taking on x of e power j omega. Right? Let's write the time domain relationships, and then let try to compute what will be the inverse Fourier transform of this delta function to write those time domain relationships effectively. Okay, so here if we consider x tilde of n is obtained by x of n, okay, convolution with, so let this be s, this s tilde of n. Okay, where s tilde of n is the equivalent of inverse Fourier transform of the inverse Fourier transform of the impulse train and frequency domain. Okay, so let us see this. So to understand this better, let us denote this particular term alone, say r equal to 0 to n minus 1, this particular term alone as, okay, yes tilde of here e power j omega. Okay, right. In this alone, let it be s tilde of e power j omega. Fine. To make this simpler, let us bring in first some of the relation that we have derived earlier. Okay, so if you remember, we have considered a function, a delta function, delta train earlier, s tilde of n, as r equal to minus infinity infinity delta of n minus rn. Okay, so let us see what's the importance of this here. So what does this mean? First, it means that you have an impulse or a unit sample sequence at 0, and it repeats, and it's periodic, thus it repeats after every n, that is again n here, so up to n minus 1, so there is no signal, and then again it repeats at, okay, 2n, and it also repeats at n minus 1, sorry, it also repeats at minus n. Okay, so and so on, so it keep repeating like this. So this is the periodic impulse train we have considered before for the discussion of finding discrete Fourier series quotients. We will see their relevance now. Okay, so if I take s tilde of k, what did we derive at that time? So we have seen that s tilde of n, okay, e power n minus j 2 pi by n k, okay, and then n ranging from 0 to n minus 1. See, if we take only 0 to n minus 1 samples, okay, which are the samples that comes in? Okay, in x, in here in s tilde of n, which are the samples it comes in? We get only these samples, okay, in 0 to n minus 1 region, and thus this s tilde of k is equal to what? 1, because n equal to 0, it is 1, and this is also 1. 1 for all k ranging from 0 to n minus 1. See, if I consider s tilde of k to be 1 for all 0 to n minus 1, right? And then if I want to write it in a in terms of the sampling sequence in e power j omega axis, how do I write? See it as, for if I sketch now this s tilde of k, it looks like 0, 1, 2, 3, 4, 5, and so on up to 0 to n minus 1. You have all ones. Okay, in this case, fine. But what is the spacing between these two? If we consider in frequency domain, if we write in k, index k, it is fine. In index omega, if you would like to see what is the gap between these two, any of these two samples, okay, how much is that? It is equal to, because the whole spectrum is over 2 pi, j e power j omega, omega varies from 0 to 2 pi, and thus there are n samples spanning 2 pi. This is 2 pi by capital N, right? And hence this can be s tilde of k can be effectively written in frequency domain or in continuous like in discrete time Fourier transform as, okay, s tilde of omega as exactly like what we have got. So delta omega minus k omega or omega naught, where, okay, so r is equal to 0 to n minus 1, where r omega naught is equal to 2 pi by n, right? So you will be taking these, if you consider continuous omega as a continuous variable, right? Spanning from 0 to 2 pi, this is being 0, right? This is being 0, and this is being 2 pi, representing 2 pi over one period of discrete time Fourier transform. Then the relation between this discrete time Fourier transform and these samples can be established like this, correct? So now you can see that s tilde of omega we have. For this, if you want to write what the corresponding, okay, s tilde of n, what do we write? It is simply equal to, okay, if you consider from minus infinity to infinity, it is r equal to minus infinity to infinity, right? It is a periodic impulse train, or it is periodic unit sample sequence. Delta of n minus r n. It repeats for every n, right? And there is an impulse at 0 and repeats again at n, okay, and so on, right? So in time domain relationships, now in this equation, okay, in expression 2, in this expression, we can substitute this. See, please note that here, initially you had x tilde of k, which is n sequence. Here, see, for example, this x tilde of n need not be exactly equal to, say, this is what we are trying to discuss here is, okay, so we are trying to discuss if we have a signal which has m samples, okay, which has m samples here. Okay, this is what we need to verify. Okay, will this be exactly equal to this? Okay, x tilde of n, if I take, say for example, if I take this DFS, IDFS, okay, for this, okay, and DFT, IDFT, inverse discrete Fourier transform for this, okay, and similarly for the corresponding thing here, will they be equal? That's what we are trying to see. Okay, that means if I sample from x of e power j omega, do I always get x tilde of n? That is the time domain expression for periodic, discrete, periodic scalar. Okay, so please note that this has how many samples? This has m samples. Okay, m samples or length of m we say. Okay, which has n length of m? The time domain expression has length of m. Okay, this is the length of m. Okay, we started with fine, and this is period is capital N. From where did this term from? This period has come from x tilde of k, because this period is also capital N, right? Because if you want to get the samples of x tilde k in frequency domain, this is the operation. Okay, this operation being done in frequency domain. By performing sampling with n samples in frequency domain. Okay, we are getting x tilde of k. This relation holds in frequency domain. The question is, if we bring in now into time domain, will it hold or not? Okay, if it doesn't hold, what's the reason? If it holds, in which, under which condition does it hold? Okay, that's what we are trying to see. Okay, so please note that this x of e power j omega has not exactly come from this sequence x tilde of n. This is a periodic sequence and this is an aperiodic sequence. But however, this this sequence and this sequence may also have, say for example, in some conditions, okay, we can relate them easily as exactly same sequences or periodic shifted version of same sequences. Okay, that we will see. So to differentiate this, let us not call it as okay x tilde of k. Let us call this as okay x reconstructed n. Okay, this x reconstructed n is the s frequency sample n. Okay, this s frequency sample n comes from inverse like inverse Fourier transform relationship of the frequency domain sampling. Okay, so you want to see if this x free in this frequency sampled n, does it has any relationship with respect to the x tilde of n? Okay, so does it has any relation to x tilde of n? Okay, that's what we want to see. Okay, hope the discussion is clear. Okay, so let's now move on. Let us see now the right hand side and then move on to the left hand side. So the right hand side of our discussion is x of n convolved with okay s tilde of n. And what is s tilde of n? We have seen that s tilde of n is nothing but the impulse train which is separated with Rn. Where does this n has come from? From period of x tilde of k. Okay, right? So because there are k distinct frequencies in the representation of x tilde of k, we have got this n. Okay. Oh, right. And this, where does this function s tilde of n has come? From the frequency domain. Okay, sampling. This has stemmed from frequency domain sampling. Okay. Okay. So, and now let us see how does this simplify? So what is the convolution with delta function? The same function, this x of n, shifts by this amount. Okay, the argument, and r varying from minus infinity to infinity. So what does this mean? And please also note that this is of length m. Okay, and so this what we have denoted this with x sample frequency spectrum sample version in time domain. Okay, that's what we are saying here. So what we have here is frequency domain sample version of time domain. Okay, sequence, right? So now you can see that. So what does this operation is doing? So you can see that if x of n, to understand this, let us take an example. Let x of n be like this. Yeah, this is the sequence x of n 0, 1, 2, 3. Okay, 3 and 4. Okay, fourth sample being 0. The length of the sequence m is equal to 5. Okay, now let n be equal to, so let x of n be like this. Okay, and let m be equal to, n be equal to, x tilde of n has a period of n is equal to 10. Okay, so what does happen when when I perform this operation, or how do I sketch x of s of n? What does it happen when I do frequency domain sampling? The implication is that this sequence x of n repeats, right, at every n gap, with after every n samples. Okay, so now if we want to sketch xfs of n, can be sketched. How do we sketch it? We start from 4, 3, 2, 1. Okay, 0, 1, 2, 3, 4. Okay, let this be the samples. 5, 6, 7, 8, 9. And where does this repeat now? This is x of n. Okay, whatever I am plotting. See, if I expand this, you can see x of n. Okay, plus x of n minus n plus x of n minus 2n. Okay, similarly plus x of n plus n, x of, okay, n plus 2n, and so on. Okay, and so on here also. Okay, so it repeats at every capital N. Same sequence x of n repeating at every capital N. Okay, right. And now where does it repeat? At capital N equal to 10. So it will repeat at 5, 6, 7, 8, 9, 10. Okay, so I will sketch the repeated signal with a slightly different color, just to differentiate. Or even completely different color, let it be. Okay, 10, oh, sorry. Right, okay. 10, 11, 12, 13, 14, okay, 15, and so on. This is, okay, so this is xfs of n, right? So, and similarly, what will happen this side? Please note that the repetition also happens this side. Okay, so same thing repeats. So minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7. Okay, so the repetition starts from minus 10. Okay, minus 9, minus 8, minus 7 also there will be some. So if you would like to put another color, 7, 6. Okay, and then okay, at 8 you can see at 2 units. Okay, like that. So I will not sketch further, but we'll put dots. Okay, so you can see that the now the question is this. Okay, this is what we have sketched simply is what is the initial x of n we have taken here, and what is the frequency sample version, okay, that we have here. Okay, and corresponding time domain, what is the information we have got? X tilde of fs. So if I start from arbitrary x of e power j omega and do sampling, and to get x tilde of k, what is that I get is this, okay, with specific capital N. Okay, so now let us assume that, so this is here, the starting point is x of e power j omega. Okay, so let us start with, so x of n, and hence, so let us write the pipeline here, x of n to x of e power j omega. Okay, after that, do sampling, multiplication with, okay, dot star with s tilde of e power j omega. Okay, and then take, right, and then take what? DFT. Okay, and that what you get is this xs fs of s. Okay, this is the process that we have done, right? Instead, if we have started with some x tilde, so this also gives it as a, while in the process you have got here, after this sampling, you have got here some x tilde of k, right? And for that you have plotted here. Okay, what you get is x tilde of xfs. So, right. So now assume that, right. So now let us assume that we let us see the other example wherein we initially have, okay, some x tilde of n, okay, given to us, or related x tilde of k given to us. Okay, so, and it has a sequence of length n. Okay, see in this example, if I, for example, if the the number of samples in the input signal, let us discuss this little later. So in this example itself, if we have a sequence having m equal to say 10, what does it happen? Say we can get m equal to 10 case, this is case 1, right? This is case 2. Even in this, we can get x tilde fs of n, right? And what will happen to the samples, sequence of samples? Say you have actually with m equal to 10, I will not sketch all the samples, but let us assume with dots. Okay, you have actually 10 samples, 0 to 9 samples. Okay, and you followed the same procedure and finally sketched it. Okay, so to have a better visualization, okay, so let be something like this. Okay, let us not go to the minute details. Okay, 0 to 10. Okay, you have now 1 to say 0, let it be here, 0 to 10. So it is 1 to 10. Okay, 1 to sorry, 0 to 9 you have, and this is 0, 1 to 9. Okay, so 1 to 9 values, right? When you sketch now the XFS of n, what will happen? Again, you will be able to get, okay, so 0, 0, 1, 2, 3, 4, and so on. You will be able to get up to 9 here. Okay, and this repeats again with 1, 2, 3, and so on. Yeah, so because the period here to repeat is capital N, right? So now take the case 3. See, in both of these cases, x of n is still retained in this xfs of n. So if you would like to get back x of n, what do? We take only one period, right? We can take one period ranging from 0 to, say for example, 0 to n. Okay, and from this period 0 to n, you can extract x of n without any problem, right? Even in the second case, okay, even in the second case, you will be able to extract the x of n taking one period of it, okay, 0 to n, right? But in the third case, let us assume that you have m equal to 15 or 12. Okay, so what does now happen? Say assume that again similar scenario, you have some signal, okay, which start from 0, keep rising, okay, and then after some time it goes up to 11, for example, at 11th sample. Okay, now if you sketch it, okay, do you think that will we be able to extract back the signal x of n from this xfs of n? See what will happen. This is 0, 1, 2, and so on. Okay, and it will go up to, say, if it will go up to, say, somewhere here. Okay, so up to 10, assume that. Okay, up to 9. Okay, this is 9. So up to 9, let us go. Okay, but now this second shifted sequence with r equal to 1 case, this r equal to, the whole thing whatever I have plotted here is for r equal to 0. Okay, for r equal to 1, where does it start? It starts, sorry, r equal to 0 goes up to 11. Not here, not just up to 9, 10 and 11. Okay, now where does r equal to 1 starts? It starts from 1 here. Okay, okay, something like this, right? So there is an overlap here. This is overlap is happening, or aliasing here is happening in the time domain. How many samples does the overlap happen? There are 2 samples from period 1 to period 2, because m is 2 times higher than capital N. Okay, that is with which we sampled. Okay, so now if you want, similarly from this side also, you can see that there are 2 samples that will be overlapping with previous period. Okay, so to get back the signal x of n, okay, even after frequency sampling, okay, to get back x of n, even after frequency sampling, what we need is that the number of samples in frequency domain has to be higher than the length of the sequence m. Okay, if that doesn't happen, okay, then we will not be able to get back the sequence x of n back. In case if the m is lesser than n, or the number of samples in frequency domain are higher than m, then x tilde of n will be exactly, say, one period of x tilde of n if you take, will be able to get x of n. Is it fine? So you can see here, in case, okay, in this case, let us sketch with even different color. Okay, so in this case, m is less than n. Okay, in this case also m is less than n, and in this case m is greater than n. Okay, hence there is a time aliasing. This is referred to as time aliasing because of frequency domain sampling. Okay, so frequency domain sampling is happening in each of the cases because we converted here and multiplying with a impulse train and frequency domain. However, you can see that the time aliasing happens in case the number of samples of the sequence is okay, is higher than the number of samples that we take in frequency domain, right? So if we take more samples in the frequency domain than the number of samples in the time domain for the base signal xfn, there will not be any aliasing. You will not be time aliasing. Okay, though there is no mix of samples in time domain, right? Please note that all these are in time domain. Okay, no mix of samples in time domain. However, if the number of samples are higher than the number of samples we take in the frequency domain, then there is a time aliasing. Thus, what we finally conclude is this. So we can get back x tilde of n, okay, will be exactly equal to x fs of n, right? X tilde of n is x tilde of k if you take sample version and take, okay, IDFS is equal to this. How do you get? This also comes from IDFT with x of e power j omega with sampling of x of e power j omega. Okay, so this x of e power j omega is obtained from x of n with length n. Okay, so and then this is with period capital N. Okay, here length m, right? So these two are equal. These two are equal. Fine. If and only if when the number of samples in frequency domain are greater than the sequence length in time domain. Okay, sequence length in time domain. Right? So to start with. Okay, then what you can do, if you take one period of x tilde of n, you will be getting x of n. So x of n, so in such case, x of n can be obtained by taking one sample, one period of x tilde of n or x tilde of fs of n. Okay, so this is also tilde because it repeats, it keep repeats. Okay, fine. So that's what, so this is IDFT. So this directly you will get only one. So I think even with, so x of n can be obtained by taking one period of x tilde of fs or x of fs. By taking x of fs directly we can write here because xf, if you consider if you consider as an impulse train, it keeps repeat. Okay, so by taking one period of x tilde of fs. Okay, right? Okay, so ideally what we are doing here is this after sampling this. Okay, so we are getting from these samples, we are getting here, this is a x tilde of k. Okay, and for that you are taking IDFT. Okay, so this you can consider XFS of k. Okay, these are the sampled version from frequency domain. Okay, so that means right. Okay, so this XFS of k is equal to x tilde of k. Okay, when provided if the period of this is greater than the length of the sequence. Okay, because this also has the say length of say period of number of samples, so n samples. So this has n samples. Okay, right. Okay, this length is m, but you have here n non-zero locations. Impulse train with n samples, you can say otherwise, n non-zero. Okay, right. Fine. So, and in case if this doesn't happen, else if n is less than m, okay, here equal to also you can get back. If n is less than m, the number of frequency samples are lesser than the sequence of the signal x of n, right? In that case, okay, what will happen? Time aliasing occurs and signal x of n, okay, with which we started, cannot be directly obtained. Okay, it can be obtained in some cases. From a period of x tilde fs of n, because anyway the period of x fs of n is smaller than the length of the sequence itself, right? In that case you will not be able to get. So here what we have seen is the effect of going from time domain to frequency domain and sampling there and coming back to time domain, and this is referred to as time aliasing. Okay, so you have actually, so if you see the sequence of steps, you have got from x of n, okay, time domain, discrete time domain, okay, signal, you have taken x of e power j omega, discrete Fourier transform, and got x of e power j omega, okay, sampled it, sampled by how did you sample? By multiplying with x tilde of omega, okay, x of omega, and sampled it, okay, to get x tilde of k. This is fs of k, sample k, and here what did you do? You took inverse DFS or DFT. Okay, we will see later that it is exactly DFT. Okay, to get x of yeah. Okay, right. So in the data discussion, we will connect to DFT. So that also the same. So this x tilde of n is equal to x of n if m is like lesser than n. So thank you.